Hello and welcome to the conclusion of the Back to Basics Season 2. Back to Basics Season 2 was all about data utilization. We spoke about data utilization from a machine-based decision support system view and from a human-based decision support system view. We introduced those two pillars, and in each pillar we introduced and explained different topics. We spoke about reporting, analysis, data visualization, dashboarding, and we spoke about machine learning, deep learning, rule engines, statistics, expert systems from a machine-based decision support. Now, it's time for the conclusion, and the conclusion cannot be done in one episode only. There are so many angles, there are so many point of views one can take on the utilization of data. We have decided to do 3 episodes. In the 3rd episode of the conclusion, and the last of the conclusion as well, and of the series as well, we will see end-to-end big data. Interesting topic, because we spoke about big data in the first season of the Back to Basics. Let's start with some basic concepts. In season 1 of Back to Basics, we occasionally mentioned the term unstructured data. Unstructured data or unstructured information is information that either does not have a predefined data model or is not organized in a predefined manner. Unstructured information is typically text-heavy, but may contain data such as dates, numbers, and facts as well. This results in irregularities and ambiguities that make it difficult to understand using traditional programs as compared to structured data stored in field form in databases. In 1998, Merrill Lynch said, "Unstructured data comprises the vast majority of data found in an organization. Some estimates run as high as 80%. It's unclear what the source of this number is, but nonetheless, it is accepted by many. It also must be clear we are speaking here of data volume, and extracting relevant information from unstructured data may represent a significantly lower volume. The challenge being obviously to understand how to extract that relevant information. Techniques such as data mining, natural language processing, and text analytics provide different methods to find patterns in or otherwise interpret this information. Common techniques for structuring text usually involve manual tagging with metadata or part of speech tagging for further text mining based structuring. Software that creates machine processable structure can utilize the linguistic, auditory, and visual structure that exist in all forms of human communication. Algorithms can infer this inherent structure from text, for instance by examining word morphology, sentence syntax, and other small and large-scale patterns. Unstructured information can then be enriched and tagged to address ambiguities, and relevancy-based techniques then used to facilitate search and discovery. Examples of unstructured data may include books, journals, documents, metadata, health record, audio, video, analog data, images, files, and unstructured text such as the body of an email message, web pages, or word processor document. While the main content being conveyed does not have a defined structure, it generally comes packaged in objects, for example in files or in documents, that themselves have a structure and are thus a mix of structured and unstructured data, but collectively this is still referred as to unstructured data. Since unstructured data commonly occurs in electronic documents, the use of a content or document management system, which can categorize entire documents, is often preferred over data transfer and manipulation from within the document. Document management thus provides the means to convey structure onto document collections. Search engines have become very popular tools for indexing and searching through such data, especially text. The second concept to remember is the called big data concept. Big data is a field that treats ways to analyze, systematically extract information from, or otherwise deal with data sets that are too large or complex to be dealt with by traditional data processing application softwares. Big data analysis challenges include capturing data, data storage, data analysis, search, sharing, transfer, visualization, querying, updating, information privacy, and data source. Big data was originally associated with three key components and concepts: volume, variety, and velocity. The analysis of data presents challenges in sampling and thus previously allowing for only observations and sampling. Therefore, big data often includes data with sizes that exceed the capacity of traditional software to process within an acceptable time and value. Current usage of the term big data tends to refer to the use of predictive analytics, user behavior analytics, and other advanced data analytics methods that extract value from big data and sell them to a particular size of dataset. There is little doubt that the quantities of data now available are indeed large, but that's not the most relevant characteristic of this new data ecosystem. Analysis of data sets can find new correlations to spot business trends, prevent diseases, combat crime, and so on. Scientists, business executives, medical practitioners, advertising, and governments alike regularly meet difficulties with large data sets in areas including internet searches, fintech, healthcare analytics, geographic information systems, urban informatics, and business informatics. Scientists encounter limitations in e-science work, including meteorology, genomics, complex physics simulation, biology, and environmental research. Relational database management systems and desktop statistical software packages used to visualize data often have difficulty processing and analyzing big data. The processing and analysis of the big data may require massive parallel software running on tens, hundreds, or even thousands of servers. What qualifies as big data varies depending on the capability of those analyzing it and their tools. Furthermore, expanding capabilities make big data a moving target. In season 1 of Back to Basics, we occasionally mention the term data lake. A data lake is a system or repository of data stored in its natural or raw format, usually binary large objects named blobs or files. A data lake is usually a single store of data, including raw copies of source system data, sensor data, social data, etc., and transformed data used for tasks such as reporting, visualization, advanced analytics, and machine learning, all concepts that we addressed in this season 2 of Back to Basics videos. Meanwhile, the concept of virtual data lake is also rising today, where data movements are performed through a data orchestration platform, letting the data in their original source and extracting them at analysis time. A data lake can include structured data from relational database, remember rows and columns, semi-structured data like CSV, logs, XML, JSON files, unstructured data like email, documents, PDFs, and binary data like images, audio, photos, videos. A data lake can be established on premises within an organization's data center or in the cloud using cloud services from vendors such as the hyperscalers. A data swamp is a deteriorated and unmanaged data lake that is either inaccessible to its intended users or is providing little value. Data science is a concept to unify statistics, data analytics, informatics, and their related methods in order to understand and analyze actual phenomena with data. It uses techniques and theories drawn from many fields within the context of mathematics, statistics, computer science, information science, and domain knowledge. However, data science is different from computer science and information science. We can today imagine data science as the fourth paradigm of science and asserted that everything about science is changing because the impact of information technology and the data deluge. The four paradigm being empirical, theoretical, computational, and now data-driven. Data science is therefore an interdisciplinary field focused on extracting knowledge from datasets, which are typically large, like in big data, and applying the knowledge and actionable insights from data to solve problems in a wide range of application domains. Related to the big data and the data lake concepts, the field encompasses preparing data for analysis, formulating data science problems, analyzing data, developing data-driven solutions, and presenting findings to inform high-level decisions in a broad range of application domains. As such, it incorporates skills from computer science, statistics, information science, mathematics, information visualization, data integration, graphic design, complex systems, communication, and business. We can also link data science to human-computer interaction. Users should be able to intuitively control and explore data. In 2015, the American Statistical Association identified database management, statistics, and machine learning and distributed and parallel systems as the three emerging foundational professional communities. Data science associated with big data is very quickly becoming a vital tool for businesses and companies of all sizes. The availability and interpretation of big data has altered the business models of all industries and enabled the creation of new ones. Data-driven businesses are worth $1.2 trillion collectively in 2020, an increase from $333 billion in the year 2015. Data scientists are responsible for breaking down big data to usable information and creating software and algorithms that help companies and organizations determine optimal operations. As big data continues to have a major impact on the world, data science does as well, due to the close relationship between the two. Now that we know a little bit more about big data, it's time for me to conclude this second season of the Back to Basics videos. Hope these were useful to you, that you enjoyed them, and I will see you next time on a probably next season of Back to Basics videos. See you soon. Bye bye.